Hi everybody, Jeremy Blum here, back with EAGLE tutorial number 2, made possible by Element 14 in CadSoft. If you haven't already seen EAGLE tutorial number 1, be sure to go ahead and check that out. Visit my website, jeremyblum.com, go to blog, and click on EAGLE tutorials, or just search for it. My first EAGLE tutorial focused on making a schematic design for a blinky board that uses a 555 timer and some LEDs, as well as a lithium-ion battery. In this video, we'll take that schematic and turn it into an actual board layout so we can eventually get it either manufactured or so that we can make the circuit board on our own. Remember, you can always get all the information for all my tutorials on my blog, or on YouTube, or on Element 14, or on GitHub. If you aren't already following me on GitHub, go to github.com/sciguy14, sign up, follow me on GitHub. All of the most recent files for all of my tutorials, EAGLE, Arduino, whatever, are always up on GitHub, as well as the open source files for all of my other engineering projects. So be sure to go check that out. Okay, the first thing we'll do today is take a look at what our end product might look like. So let's go ahead and open the completed project that I've already done. This should give you some idea of what it'll look like. This is our battery, 555 timer, some resistors and LEDs, and some passives that determine the oscillation rate of our 555 timer. So here's an idea of the finished design. When you have a board and schematic file, EAGLE will automatically link them together and open them at the same time. So let's go back and look at the one that we started to make next week, blinky.schematic. So we'll open that up, and it'll open up the schematic that we made last week. This should already look familiar to you. In my first video, I showed you how to make this schematic. Once you have this schematic going, you can click this button right up here, the board button. This will take the schematic and turn it into a board that you can then begin to lay out so that we can eventually get it fabricated, solder on the components, and have a working circuit. So click the board button. It'll ask you if you want to make a new board from the schematic. Hit yes. And it's opened up our board. It's already given us a dimensional area to start putting things in. This is basically the size of the board, and it's put in all of our components, although they're outside of the board area. One important thing to keep in mind with the free version of EAGLE is that you can't move components around outside of the board area. It'll pre-populate them there, but if you try to drag them around outside of the board area, it'll get mad at you. There's certain maximum dimensions that are allowed by the free version of EAGLE, so you'll have to keep the dimensions of your board within that. The Blinky board is very, very small and is well within those dimensions. You'll also notice these yellow lines here. These yellow lines are called air wires and correspond to connections that you made in the schematic. They basically tell you how you have to wire up all these components to each other so that you have the electrical connections that you need, that you already defined in the schematic. So these are all of our parts. The next thing we'll do is go ahead and get them on our circuit board, maybe get some nice silkscreen effects on there, and take it from there so that we can eventually get the board manufactured. Okay, so the first thing that we should do is go ahead and drag these into a kind of position that we want them. I'll more or less emulate the design I already did with the battery down at the bottom. So to drag components, just like you did before, click once on the move button, drag them around, and then click again to release. If you want to rotate an object, again, just like in the schematic, click the rotate button and click it to rotate it. Let's move all of our components around to convenient locations. And part of this will be up to you, but really you'll want to define it based on what your connections are like. You'll want to place the components so you can draw the shortest connections possible, and ideally so that you have the shortest amount of vias possible. A via is a connection between the top and bottom layer of the board. The circuit board that we'll be designing today is a 2-layer circuit board, which means there's a layer of copper on top and a layer of copper on the bottom. Some circuit boards can be much more complex than this. Some boards have 8 layers of copper or more. Often some of those inner layers will be ground or power planes that are used to route various voltages or to connect the grounds around the board. This is common on things like computer motherboards, things like that, where you'll find extremely high numbers of layers and high density component packing. If you recall from the first video, we chose 0805 resistors and capacitors, which is what's determining their size here in the package that we're using. There's a couple layers that we should talk about, and I'll just make sure they're all on for now. If you click the layers button over here, you can choose which layers you want to turn on. There's a lot. You don't need to worry about all of them, but let's talk about some of the important ones. I'll turn them all off for now, so you can get an idea of which is which. Top defines the top copper layers. These are where basically you're going to want to have connections between various components and where the pads of each of the components are. The bottom is all the copper that you'll have on the bottom. I'll enable it, but for right now, we don't have any components that we've assigned to the bottom or any wires that we've drawn on the bottom, although we will later. Pads and vias will partially define connections between the top and bottom layers. Again, we'll do that later. Unrouted, we've already seen. These are the air wires that Eagle draws us to help us figure out where everything is. Dimension is the size of the board. These are all important layers that will then transmit to the board company that will allow them to fabricate the board easily because they'll know what layers each thing is assigned to. T-place refers to a silk screen that's printed on the top of the board that will show you where to place the eventual components on the board. Keep in mind that if you have something like this where a silk screen is on top of pads, usually the board manufacturer will make sure to remove it over the actual pads so that you can solder to them. B-place is the same thing on the bottom, but we don't have any bottom-mounted components today, so we won't see that. T-origins represents a crosshair that allows you to actually drag and find all of the components. T-names and T-values will correspond to the names and values that are assigned to each of the components. The name is a reference designator, often that you'll find in a bill of materials that allows you to find the component on the board, such as IC1 or C1 or R4, whereas the value is the actual value of the component, if applicable. So with a resistor, it'd be its resistance in ohms. With a capacitor, it'd be a capacitance value in farads or microfarads. I frequently remove the values from the board. I'll show you how to do that later, because you'll generally just reference the bill of materials if you want to see what value is in a given location. But that's kind of up to you. There's a lot more here. I won't go through all of them. T-stop is used to define where openings are for you to solder to, basically in the top of the board. T-cream, we won't care about this too much. This is generally for automated manufacturing. It determines where the aperture openings are for when we're applying solder paste for reflow ovens, when you're having all your components automatically mounted for you. We'll keep going through these. A lot of these won't actually apply to us. Some components have T-glue. You'll see some of the resistors have them in the middle. We, again, don't really ever use this too much. And there's a whole bunch more. Again, I won't go into all of them. Drills and holes will be used to define holes that we want drilled in the board, for example, if you want mounting points. And there are a whole bunch more. T-docu is a layer shown by a bunch of components that will not be printed on the eventual board, but help to show you where the actual component sits. I like to personally change T-docu to be bright yellow so it's easy for me to see. Knowing that the yellow will not end up on the actual board, it's just meant to show you where the actual components sit on the footprints so you don't end up with anything accidentally overlapping. Okay, those are the really important things for now. There are a few others that we may talk about later. For now, I'll just leave all the layers on. Now that we have an understanding of our layers, let's actually go ahead and move all these things around to some reasonable locations. Okay, so like I said, you can use the mouse wheel to zoom in and out. You can also click this zoom select button to zoom in a particular area by selecting it. Okay, we'll put the battery down towards the bottom, the 555 timer a little bit above that. We'll mount some of our capacitors down over here, and I'll just go ahead and start moving these around, and you can see where I'm putting them. Okay, to me that seems pretty good for now. We might end up moving things around a little bit more as we see where they should go. A very important button is called the rat's nest button, or this basically calculates the shortest airwaves between components, air wires. Once you have the parts where you want them, click the rat's nest button and it'll draw new lines defining where everything is connected. That should make it a little easier to start actually drawing the connections on your own. There are a few ways that you can go about actually making the connections between these things, which I'll talk about now. You can use the Eagle's auto router, or you can do all the routing manually. You can also add things like ground pores and define net classes that determine certain thicknesses of certain wires, how far apart they have to be from each other, and things like that. The first thing we should do, though, is go ahead and get the dimensions of our board correct. So let's go ahead and move this down and in so that we get our board to a more reasonable size. Okay, that's looking better. However, I always like to keep the origin all the way on the bottom left. That makes it easier when you actually generate the output files for your board house to make sense of where everything is oriented. So remember, if you hold Control and right-click once, you can move a group. I'll move it back to the origin there. And we might end up expanding this or whatnot later on. Okay, the next thing I'm going to do, which I didn't do in my original board design, but I'm going to show you guys how to do now because I think it's useful, is to define ground pores. And what a ground pore is basically on the top and bottom layer, we can define that the entire surface of the board that doesn't have particular wiring going through it will be defined as a ground plane. Ground plane is nice because, well, for a few reasons. It dissipates heat. You often have a lot of connections to ground on your board, and it makes it easier to connect all the components to it. And it's good for RF emissions and things like that too. More frequently on larger, more complex boards, you'll also see grounds in internal layer planes and things like that. But for now, this will work pretty well. So to define a ground pore, we'll draw a polygon around the entire thing. It doesn't have to be exactly the appropriate dimensions. Doesn't really matter. Before I do that, though, I'm going to turn the grid on so it's a little bit easier for me to see this. So I'm going to turn display on. Okay, now we can kind of see a grid that we're working with here, which I think is a little bit nicer. Okay, so I have polygon. I'm going to do this on the top layer first. I'll click once and draw it around. And as you kind of draw around, you can move the screen around and whatnot and zoom in and out. Okay, that's it. You'll see it turns into a dotted line when it's complete. The next thing we'll want to do is change the name of this polygon to ground. And what that does is it makes a connection between this polygon and the points that we have defined as ground in our original schematic. If we go back and look at the schematic, we see that we have all these ground connections defined. We'll basically be adding this to that list by doing that. So I'll click on define the name of an object. Click on this. Choose to do it for this polygon and rename it to ground, GND. I'll hit OK and it's now connected to ground. You'll notice nothing has changed yet. That's because we now have to hit the rat's nest button. Once we do that, it'll fill in the ground pore, and you can see that it's left some spaces around all of the components, but connected to grounds where necessary. So for example, this side of this LED was connected to ground. We can see it's used thermals, which are basically thermal reliefs that make it easier to solder this piece down, but it has connected this particular pad to ground and left an opening around the other pad so that we can draw wires to it and whatnot. The reason for the thermals here is that when we have a large ground pad like this, it's going to sink a lot of heat. So when you're soldering parts on, there's a larger surface area for the heat to dissipate over. And if you want to be able to solder this part easily, the thermal helps to make that a little bit easier, as opposed to having the pad completely connected all the way around to the ground pore. Next thing I like to do is clean up the silk screens before I actually get everything wired together. So like I said, I don't really like to show the values on here. I don't really think it's necessary. So you'll notice right now when I move parts around, the values and names follow them. If I want them to become separate so I can move them around and put them where I like on the board, I can click this button called Smash, which separates the name and value from the part. Not permanently, but it allows you to move them around and control them independently. I'm going to quote-unquote smash all of our components here by clicking on their origins. Once I've done this, if I choose to, I can delete their values. So I click the delete button and delete some of their values because I don't really feel like I need these on here. I know what they are from looking at the bill of materials. Okay, and I'll leave CR 1220 on there because, I don't know, why not? And this also allows you to move the names around so that we can get them situated like we want. If you're finding that things aren't moving exactly to where you want them to, you can redefine the grid. So the grid determines where you're able to put parts. If you hit grid on the top left here, it allows you to actually gain control to those sorts of things. Right now it's on a 0.05 inch grid with an alternate grid of 0.025. What alternate means is if I'm moving a part around like so, and I want a little bit more fine control, I can hold the Alt key and it allows me to move it in the alternate grid, which is not the grid that's actually shown here. Alternate is not shown. If we want to get a little bit more precise, For example, we could change the normal grid to 0.025 and the alternate grid to 0.0125, which is half of that. We can see that the grid spacing gets smaller, and we now have some kind of finer control over where everything is, which might make it easier to situate things where you like. If you want to get really crazy about it, you can hit the info button, click on an object, and actually define its position by typing in manually. So if I want this at 0.15 and 1.8, and this is from the origin down on the bottom left there, and hit apply, it'll move it to exactly that position. And then I can do whatever I want with it, move it around more, whatever. You can also independently rotate names so that you can situate them properly on the board. And in the new version of Eagle, you can define where their origin point is. So right now it's bottom left, but I could also define it as bottom center, for example, hit apply, and now it's oriented around the bottom center of the text. You can do this for all of them, make everything nice and pretty. It's not really super important for right now. I'm going to go ahead and rotate this around, and you'll see it hasn't updated the ground pour yet. You'll have to hit rat's nest again, and it'll do that and redraw the lines and good things like that. Okay, great. So I think we're just about ready to actually start routing this now. So let's go ahead and do that. So before we're ready to actually start auto routing, we have to make sure that there's some rules in place so that it knows how we want it to do it. Right now we only have one net class defined. I'll explain what that is in a minute. If we go to edit net classes, we can see the net class default here. The width, drill, and clearance are certain specifications for how the auto router is allowed to do the net class. Since we only have one net class right now, this is easy. I'm going to make all of the traces about 12 mils wide, make the drill about 20, and clearance, let's say 10 mils. These are pretty conservative. Most manufacturing houses can do much smaller traces than this, keeping in mind also that your trace width will be determined in part by the amount of current you have to push through a particular line. In more complicated board designs, you'd often have many more net classes, for example, a power net class, for example, if you have a high voltage rail, and you might define that to be a width of 50 mils because it carries a lot of current, and to have a larger drill size. Similarly, if you're using differential USB signals, you might define them to have a very large clearance from other signals so that you can make sure you don't get interference on those lines. But for now, this will work fine. So hit OK. Alright, now we're ready to start the auto router. Click Start the auto router, and it'll bring up a few options. This is basically defining what layers it's allowed to use and how it will prioritize each one. As you can see, my version of Eagle can handle up to 16 layers, but the free version is only 2, so you might not see all this. But we'll allow it to use the top and bottom like this. Routing grid, I'm going to decrease down to about 10, so it's able to push things closer together. Sometimes with higher routing grids in mills, you might run into issues with it not being able to route everything. All these other tabs define basically all the optimizations it tries to go through to get the best routing possible. You generally want to minimize vias and things like that. For now, we'll hit OK, and we'll see how this does. Okay, so it'll iterate through a bunch of options, and we can see it doing that, and then it'll finish up. Now we can see that it's only 94.7% finished. So if we look at the issues here, we can see that there's a ground pad in here and a ground pad out here. They're both connected to ground pours, but those ground pours aren't actually connected to each other. Now, there's a very easy way that we can solve this. We can either draw our own connection underneath, or we can go back to what we did before and define a ground pour on the bottom level. So I'll draw another polygon, and we'll wrap it around here. Make sure it's on the bottom layer, which is blue. Okay, just like before, I'm going to define this as ground. Okay. All right, so I'll hit rat's nest. Still not going to do anything. That's because there's still nothing on the bottom that is actually connected to ground. To add something, we'll do it in a similar way we did it before. I'll click via over here and manually add a via. I'm going to choose to make mine round. It's already picked a drill size of about 23 mils, which is fine. And I'm going to click and put it right here. Still not doing anything. So we hit name an object and choose to rename this via to the ground connection. We'll hit OK. It'll ask if it wants us to connect it, and it'll connect it to ground. Now you can see that the bottom has been filled in. That's because this via is connecting the top ground pour to the bottom ground pour. So it's making an electrical connection there. Now the last thing we have to do is bring it back up in this area over here so it can get to this ground pad. So you can either define another via, or you can just hit the duplicate button, duplicate this via over here, which will keep it on the ground layer, hit rat's nest, and you can see the connection goes away because now it's connected down to the bottom through these vias. Normally, what I like to do when I have a board with ground pours on both the bottom and top side, I like to place a bunch of vias around to make sure that there's a good connection between the two. Again, this is more important with more sensitive board designs and more complicated electronics. It's not super critical here, but just for the hell of it, I'll place a couple around. Okay, this is looking very good. So we have our board routed, and really at this point we're ready to bring it into production if we want to. There's not that much else we have to do. However, I do want to show you guys how to do some manual routing. I won't manually reroute the whole thing, but let's reroute one or two components. So let's take, for example, the connection from this pad to this pad, from the capacitor to the 555 timer. If we hit this I button, it'll make it easier to see the complete connection path. So we can see that this capacitor is connected through to this pad, and that underneath here there's actually the red line on top, the blue line underneath it, which goes to this pad over here, and then back up to this resistor. What's also really cool about Eagle is it'll highlight this in the schematic too. So if I move this to the side, we can see that that same connection is shown in the schematic. This is what we defined as CONN in my previous video. So that's really helpful about Eagle. Makes it really easy to debug problems. Let's go ahead and rip up part of this and redraw the connection on our own. So we can hit the rip up button here, and if you click each part of the connection, it will quote unquote rip it up and replace it with a rat's nest. So you can do this for each part, or if you click on the same part that you've already ripped up twice, it will remove the entirety of the connection. So let's do that for now. And then to route manually, we'll click this route button. We can see that the width of the line here is defined by 0.16, but we were using 0.016, but we were using 0.012 or 12 mils for everything else, so we'll use the same thing. And I'll set the drill width here back to 20 because I believe that's what we were using for the auto router. So when you're actually ready to route something, you have to select the layer that you want to start on. In our case, we only have two options, top and bottom. You can also choose how the wire is going to follow itself and how it's going to bend. I like to generally use not 90-degree connections. This is more important for high-speed signals. This is a very low-speed circuit, so it's not an issue. But on higher-speed systems, you have to worry about reflections in the line if you have a 90-degree turn like this one. But just out of habit, I pretty much do it for everything, so I'm going to click on this one. Okay, next you'll click on one of the ends that you want to start connecting. Click once and it'll start to draw a wire. It doesn't matter if we draw through the ground port all right now. We'll deal with fixing that later when we hit rat's nest. So I'll click here, we'll draw it up. Now I can go to this point here, but I also want to go to some of these other connections that I have to make. So I'm going to, while I'm not holding the button or anything down right now, I'm going to go select bottom over here, and it'll create a bottom. As soon as I've finished making this bottom, it will indeed place a via there. Be careful not to cross other things on the bottom layer. So right now we can see here that we have a wire on the bottom layer, so I don't want to cross it because that will make a connection between the two things, and that's not what we want at all. Okay, so I'll bring it up underneath the chip here, just like that, bring it up and around. We can see it's defined a via for us now here too. And now I want to bring it up to this connector right here, but I want it to make the bend first, not towards the end. To do that, you can choose a different bend option, and we can see now that it adds the bend back at the beginning of the wire. So I'll add this over here, keeping in mind that we again have to go back up to the top layer in order to actually connect to it. So I'll do that, and we can see that we're now connected there. To make sure it shows up, hit rat's nest again, and we can see that we have the connection pretty nicely defined. Okay, but there's still a few more places we need to connect. We need to connect to this pad, for example. So let's do that. We have the top selected, click the pad, and we'll just go ahead and route it over to our via. I'll change the bend method, and perfect. Click rat's nests, and we can see it made its way through the ground port over to that via. We have one more connection. Now Eagle is telling us it wants to connect it down to the bottom layer. Obviously that's not going to work. You can either put it there and move a via there, being careful not to let that via overlap with other wires, or we can bring it over to this via, so we'll do that. Click on the pad again, bring it up, and bring it over to this via. And now we're connected. That's all there is to it. So we have our board totally wired now. We used the combination of the auto router and some manual routing. Personally, whenever I do board designs, I manually route everything, even very, very complex boards. That's because auto routers aren't exactly perfect. Eagle's is pretty good, and for simple board designs like this, it's great. But when you're dealing with high-speed signals or differential pairs, things like that, doing manual routing is generally what I prefer to make sure I get exactly what I'm looking for. But this is looking excellent right now. The last thing we'll do is move some of our silk screens around to get them like we like. Okay, these are looking pretty good. I'm pretty happy with this. Let's say I want to get batteries centered, for example. I showed you how to do this earlier, but here's a quick refresher. I'll change it to go around the top center. Okay. And it's actually showing up on the bottom because if you'll recall earlier, we flipped the battery around. And now I can't get it perfectly centered to where the battery is. I can do that by manually putting it onto a grid that I want. So like that, for example. Perfect. That's looking great. Okay. Our board is routed, and it's pretty much ready to go. If you want to add some more finishing touches here, you can add your own text. So click Draw Text, enter your name, so we can say Jeremy's board. Now, be careful, because right now this is defined on the top copper layer, which we obviously don't want. We want one of the layers that we'll define to be related to the silk screen. So I'll choose top place, which is what I usually choose. Top names also works. It's just a matter of what layer it puts it on. Later on, when you generate the files for the actual board manufacturer, you'll choose what layers are assigned to which parts of the board, like the silk screen, for example. I'll put that down there, and then I'll rotate it and move it to where I want on the board. It's also generally good practice to put a revision number on your board, especially because with most board designs, you'll be making several versions of it as you work out bugs. So I'm going to call this Rev A. And I'm going to put Rev A down right here. Nice and easy to see. You can hit Escape, and you'll leave the Enter Text wizard. Okay, I'm feeling pretty good about this board right now. There's one more thing I want to add. Let's go ahead and add a hole so that we can mount it to something. So click the Hole button, and you can choose the drill size here. What you choose is up to you, keeping in mind we're working in inches right now. You can change it to millimeters by clicking on Grid. Let's go for about 43 mils. Should be good. And I'm just going to put one hole down in the bottom corner so that I can kind of nail it to the wall or do whatever I want with this. Maybe put it on a keychain. You can always edit the size of a drill hole by clicking Info, clicking on the hole, and adjusting the drill size. So if you decide you want it bigger, just go ahead and make it bigger. Okay, now our drill is bigger. If we hit Rat's Nest, we'll see that it moves the mask out around from it so that we're not accidentally shorting anything out if we put a metal screw through it or something like that, because that would be most unfortunate. Okay, board is done. Before we actually wrap it up though, let's go ahead and do a design rule check. This is basically Eagle's way of checking through the board and making sure it's actually going to be manufacturable. This is a really important step in any design process. For right now, we'll use the default DRC checking rules, which should be fine. We'll see how they actually come out and how we do. So hit check. Okay, so we come up with a whole bunch of errors. So let's see what these errors are. One of them is drill size. So we defined our drills to be, for our vias, to be about 20 mils, I believe. My suspicion is that in the design rule check, we've set the sizes for our holes to say that they have to be larger than that, basically. So yes, we've set our minimum drill to 24, but we know our board house can support 20 millimeters. So we'll say, don't worry, it's okay for the holes to be 20 millimeters. So let's change that. Yeah, and we can see that those drill errors went away. The only error we have now is a stop mask, and this is a pretty common error. So what's happening here is it's upset about some overlapping layers, in particular the silk screen that overlaps with exposed copper. It's going to get upset about this because obviously you don't want the silk screen printed on top of the copper that you're going to be soldering to. However, once again, most board houses, printing facilities, whatever, will automatically handle removing the silk screen when it's over the copper. So we can actually ignore stop mask errors. I've literally never had an issue with ignoring these with any production house I've used. And that's what all these are referring to. So we can hit fine, clear all, those are gone, and we're happy, and we're good to go. So you've finished your board design. Congratulations. There's a few more things that you can do, lots of other options. I won't go into all of them now, but I do want to make you aware that there are user language programs that can do things to adjust your board design and do all kinds of neat stuff. For example, if we go to Command Renumber, we can renumber things in the order of the board. So it's with a very large board with lots of components, it's easier to find the parts that you want because they kind of go in order. So we'll hit Renumber. It changes the layers, and you can see they renumbered it. So like it's R1, R2, R3, and R4, kind of going down from the top left. It's disabled a bunch of our layers, so we can hit all again and show all of the layers. But that's basically it. You've just designed a board in Eagle. Congratulations. The next step will be to actually get this manufactured. That could mean generating Gerber files. It could mean using the PCB quote tool in Eagle to get it sent out. Or it could mean printing it out on a laser printer and doing it yourself. Again, that'll be more difficult with two-layer boards like this design, but it's still 100% possible to do that. Okay, so that's it for this episode of my Eagle tutorial series. I really hope you guys enjoyed it and that board design makes a little bit more sense now. In the future, I may go into more details on specific aspects of board design, how you have to be careful about things getting too close to each other, and differential signals, high-speed signals, the coupling capacitors and their importance, power planes, things like that. But for now, this is a simple, high-level overview. Next time, what we'll do is we'll talk about actually how you export this design, how you get it manufactured, and maybe if you're lucky, even how you can get a 3D render of your board design using some very cool user language programs. Okay, thanks everyone for watching. I hope you enjoyed it. All of the source and all the design files will of course be on my website and on GitHub, and please let me know if you have any questions. Thanks for watching.